Okay, so this is again from the 180 website, but I'll post it. If you guys think it would be helpful, I'll post it on your site. But we got things like this.
Pigeons?
I thought they said it was crows. Yeah, that's not good right there. I tell you, that bird probably is not alive anymore there. Okay.
Food for the homeless.
What?
Food for the homeless. It's already cooked.
This is kind of cute too. Again. Almost looks like our substation. See how they have that nice little pad where you can stand on? Oh, there you go. So obviously, if you open that disconnect, there are not going to be happy birds there. Okay. And then this is one that students always want me to show. It's from Southern California. I don't remember if I show. Oh, Sub-Saharan Africa, black mamba. Okay, there you go. Those are all good. That's a nice video there. Rat in a substation right there. Fire ants. That's an interesting little.
So what do they do with the ants? They dig all that out and vacuum it out?
Yeah, you'd have to. But I would look at the fire ant video before you did anything. Okay, because yeah. So now mine wasn't from E-Bomb's World. It might have been a little bit nicer copy, but did I show you guys this one already with the bear? Okay. Here you
go. Crowds gather as a California black bear left stuck on top of a power pole.
What?
Did they shoot it with like a tranquilizer or something?
No, you just got zapped, dude. Can you see it?
No.
Now he's gonna get zapped some more.
The inevitable happens as the bear is shocked by the live wire and loses its breath.
So notice he gets zapped once right there. See? That's what slowed him down the first time. Oh, what the heck?
Amazingly, the bear survives the shock and the fall.
The shock and the fall. See, the bear wasn't electrocuted, so that's a good thing. So boom, 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 and then snake on a. Oh, this one's kind of sad. No, full-size gorilla. I think, or a chimp. That looks like a gorilla to me. He was just yawning there. This guy they shot. What the heck? What are you guys shooting me for?
What is that?
I don't think it's Georgia. And it looks like they've got all these lines turned off, but I don't think they have the lines turned off on the next circuit, as you will soon see. Yeah, you see how many circuits they have there? That would be India or someplace like that. Oh. I think he got zapped right there. No. But he survived too, so won't spend any more time on it. But pretty sure he did. Yeah. Okay. So you guys want me to post that on your Educat page too? Sure. Okay. But yeah, I get a whole bunch of stuff from these guys, so I'll be posting more of that. I can't post the PDFs because they charge you for the PDFs. So okay. Oh, that's no fun. Austin, you're here. Aaron, you're here. Wes, you're here. Clay, excuse maybe, just this time. COVID-19. What are we gonna do if we get COVID-20, eh?
I don't know.
It would suck. Okay. Oh, that's right, I'm being recorded. I should watch my phone. Okay. So this is the last topic in this chapter. This is cap bank protection. We've gone through transformers and reactors, and now we're going to do cap bank. Peter was reminding us that we had cap banks back in 180, where we had to size them and everything like that. So if we look at, and there's also a paper on cap bank protection. So for both transformers and cap banks, I've got ancillary reading material. The textbook is, I think, okay on both, but it's also a good idea to look at somebody else's viewpoint. So there's a IEEE paper on capacitor bank protection that I've got posted on Educat too. Yep. That's a dead shoulder. Okay, so this is the case. We're going to have insulators come out at the top. Okay. Inside, we're going to have, we could have just one large resistor, or we could have a series of resistors. Okay. And then we're going to have our capacitors. And we'll have multiple levels of capacitors. Okay. I'll just put 3 dots down here on the bottom, so we can have multiple levels of capacitors. So
What do you mean by, the group level?
okay, I'll get into that, but that's a good question. So each individual one looks about the size of a pop can or a soup can. Okay. And like I said, you can have 2 leads coming up, right? And sometimes have resistors right there, okay? So again, this is about the size of a small, well, it's actually, most of the time, it's bigger than a Pepsi can. Let's say it's about the size of a soup can, maybe half a Guinness tall. Soup can or large baked beans, something like that. Then what we'll do is we'll have a bar going across. Okay. Individual leads right here. Resistor between the terminals. So there would be one level, okay?
Can you have as many as you want, like on one level? Or
Yeah, you can have a dozen if you wanted to. Let's look at this. We got this. There's 4 in one level. Each can is, let's say, 10 microfarads. What is the total capacitance? So if each one of those cans are 10 microfarads, how many do we have here? 40, right? So that's 40 microfarads. That's 40 microfarads. And that's 40 microfarads. Everyone see that? They're 10 each. Okay. So what's going to be the total value of C? Right? So when they're in parallel, they add like resistors in series, right? And when they're in series, they add like resistors in parallel. So, oh, KV, man, KV. Okay. So what's going to be the total withstand? It'll be 3 times 5 kV or 15 kV. Want to see how I got that? Oh, he's got more hooks and everything now. Look at all that cool stuff. He must be doing a rigging class. Hope it's not on the elections, you know.
Yeah.
That's a silly joke. I'm sorry. Okay. So total withstand is total current how much? 40 amps. Does that make sense? So we size each one of the cans is going to be exactly the same size because we want them to equally carry current and we want them to equally withstand voltage, right? Is that making sense? How I came up with that? So that's what's inside the capacitor bank. You have these units, right? Then you could have 100 of them stacked up if you wanted to, right? Well, it would be a factor of, it would always be a multiple of 3. So you could have 99 of these guys, 33 on each phase. Okay. Each one of them can withstand 15 kV. The cases aren't grounded. The bottom case would be, right? But then you have insulators for every case above that. So each one can withstand 15 kV. So you got 33 of them. You can see how you can get up to 345 kV, right? Okay. Same thing with the current. Each one of these units can withstand 40 amps. If you need more, you'll put 3 or 4 of these units in parallel. Okay. Now, one of the things that different manufacturers have, some have fuses interior to the unit, and some have fuses that are exterior to the unit. Okay. There's a thing called cascading that if you have interior fuses, you're not going to have a cascading problem, because if every one of these capacitors, these individual cans, have a fuse on them, one can shorts out, the fuse on that can, will open. Okay. Now, the other 3 cans would have to handle that increased current, right? So you have 13 amps on each one of those, through each one of those capacitors. That might cause a problem, but a bigger problem would be is if one of these capacitor cans shorted out and it wasn't fused, then how much voltage are you going to have across that level? 0, right? If one of these capacitors short out, there's no voltage across that level, and now you can have more voltage across the other level, which will cause one of those guys to fry. And that's why it's called a cascading event. One fails, it'll cause another one to fail, which will cause another one to fail, which will, eventually the whole thing is just going to fail. Okay. If they're internally fused, those manufacturers say, well, hey, we can save you some time, and then you can just monitor the capacitor. And if it's out of spec, then you know to take that can out of service, open it up, replace the fuses, put it back in service. Okay. The manufacturers that don't put fuses on there say, don't ever open up our capacitors. If it fails, it fails, because it's going to fail catastrophically. And it's funny because different manufacturers, our way is best, our way is best. And then they get bowed out by their competitor. Now that same salesman is now telling you, no, the other way is best. So, but yeah, Cooper, when I was working in industry, Cooper Power, and GE were the 2 big in America capacitor manufacturers. And I can't remember which one was fused and internally fused and which one was externally fused. So we've got 2 IEEE standards that govern capacitor banks. Remember, for circuit breakers, we've got C37. Okay. But for capacitor banks, we've got 2 different standards. According to the standards, are continuous operating voltage. They should be able to continuously operate. Okay, so V nominal RMS times the square root of 2, what does that equal to? That's V peak, all right? And so we're saying 120% of V peak. So we've got a 60 hertz waveform. And what we're saying is that there can be all these harmonics on top of it. Okay. And that highest peak should not be 20%, has to be less than 20% of the nominal peak. Is that making sense? Okay. So it should be able to withstand 135% of rated current, again on a continuous basis. Does that make sense? Okay. So nominal voltage is V rated. So not less than 100% and no more than 115%. So what the manufacturers could do is they could put more capacitors in there, right? And so they don't have to worry about ever being less than 100%. But then you got too much capacitance on there and the voltage is going to climb too high, okay? So the manufacturers have to be held within a tolerance. Can't go less than 100%, can't go more than 115%. Okay? So when you've got rated voltage, that's the VARs that you should have on that guy. And remember, Q equals what? E squared over X. Okay? So if we know what rated voltage is, that tells us what our impedance of the capacitors has to be. Usually those are the two numbers that you're looking at on capacitor banks. You're looking at the kVAR or the mVAR and the rated voltage. Is that making sense?
Yeah.
Okay. Already talked about external and internal fuses. So let's go into configurations then. We got a grounded Y. Just like the name implies. Added benefit, this configuration absorbs the surges. So it will also act as a filter. This is in general a good thing. It can also be a bad thing. If you've got a source for high frequency current close by, this will act as a sink to that. Making sense? Okay. Another positive for the grounded Y, easy to put two banks in parallel. Okay. The other configuration would be ungrounded. Y or delta. Problem there is that you lose that surge capability. Okay. So those are the different systems that we have. I guess I got 3 minutes and I can finish this up. So you can put a CT on the grounded neutral. And if you've got any current in there that tells you that there's a problem with your capacitor banks, that one is, let's say you have some cans that are shorted in one of them, that'll be unbalanced and you'll get some current there. This system will work with both grounded and ungrounded Y. So you have PTs in the middle of the capacitor bank, and basically it's the same thing as an 87 for current, but this is a voltage balance. Here you can put a 59 relay in there. Anybody remember what 59 does? Okay. And then you could have, if you've got two banks in parallel, you can put the CTs on them.
Up a little bit.
Oh, sorry. Oh. I didn't see that. There we go. Okay, then that would be a 51 right here. 51 is a time over current. Okay. So that means if we have more current, these banks should be the same size. So we should have the same amount of current going through both of these guys. Now, we could have unbalance caused by an unbalanced fault someplace on the circuit. The idea is that these two currents should cancel each other out. When they don't, then we want to trip by time over current relay.
You know what day the final exam is?
What?
Do you know what day the final is?
The day of the final. I will find out and I will text you guys. You saw that I posted the third exam, right?
Oh, no, I haven't looked yet.
I sent you an email on it.
Oh, yeah, I got the email. I didn't
Yeah.
know. I thought you meant every time.
Yep. No. For this class, since your lab time is a different time, that's why I send you emails on it.
Yeah.
Okay, so I'll look into when the final is going to be and I'll post that.
Sounds good.
Okay.
See you after that.
Yep, take care.